The first thing we did is parabolas. We graphed quadratics. Ax squared plus bx plus c is standard form. You could have it in standard or in vertex form, which we're going to do on the next problem. Standard form looks like this. I've asked you for multiple things here. The first thing is axis of symmetry. The axis of symmetry is negative b over 2a. Negative b over 2a. So when I'm solving for the axis here, I am going to use that negative 2, which is my b. So that's going to become positive 2 over 2 times a, which is negative 1. So my axis here is negative 1. At negative 1, you're going to graph this dashed line so you can see your axis of symmetry. All right, I am now going to find my vertex. I already have the x value of my vertex. The x value of my vertex is my axis, so that's negative 1. If you have x, to solve for y, you just plug it in. So negative, and I'm going to plug in a negative 1 and square it, minus 2, plug in a negative 1, minus 5. Order of operations, do those exponents first. This is one of the most common mistakes that I get with a problem like this. I'm going to square the negative 1, which would be positive. Then I'm going to apply the negative, which would make that a negative 1. Negative 2 times negative 1 is a plus 2, and then a minus 5. So I end up with a negative 4 here, which is my y value of my vertex. I'm going to graph negative 1, negative 4 as my vertex. All right, my y-intercept is the easiest thing to solve for when it's in standard form. It is just 0 and c. So I'm going to have 0, negative 5 here, which is this. Then I want to sketch my graph. Remember, you can mirror that y-intercept over, and then you can sketch that graph. It is a U type, like a curved, and it's not a V. It's not sharp. And I know this should point down. How do I know this should point down? So for inequalities, it's exactly the same. I just chose one that was in vertex form so you could see your vertex form, because this is also asking for axis, vertex, y-intercept. So when it is in vertex form, you have a times x minus h squared plus k. Your axis is h, but remember, your original formula has a minus. So that h is going to look like the opposite of what it originally gave you. Your vertex is hk, and your y-intercept you have to solve for. Plug in a 0. All right, so let's look at this one. My a is the number in front of my parentheses. Remember, when you don't see one, that is a 1. My h here is negative 2, right? Because it's the opposite. And my k is a 1. So when I'm finding my axis, that's going to be just negative 2. My vertex, that's going to be negative 2, positive 1. So just like I did on the other one, I'm going to graph my vertex with that dashed line. I'm going to graph my vertex, or my axis with the dashed line, my vertex with just the point, negative 2, 1. The y-intercept is the one that you have to solve for in this one. So y-intercept, you actually need to plug in a 0. It's always going to have a 0 as x, so we're going to go through 0 plus 2 quantity squared plus 1. You're going to do order of operations here. It's a plus 2. So what is my vertex? My y-intercept here is 5. So my y-intercept is 0, 5. Again, I can tell that this should point up at the very beginning because my A was positive. I can mirror that over. It's 2 away from my axis. I can do 2 away over here. Now at this point, it's going to be different. I'm not just going to draw my line. Before I do that, I need to figure out if it's dashed or solid because this is an inequality. So I'm going to look at this and I'm going to say it is just less than. That means it is dashed. Remember, when it is less than or greater than, I do a dashed line. When it's less than or equal to, greater than or equal to, I do a solid line. When it's my less than, I am going to shade below it. When it is my greater than, I'm going to shade above it. So for this one, this is just less than, which means I am going to dash that graph. And to decide my shading, it is below it. Well, I look at my vertex and say, which side of it is below it? Well, this side of that graph is below, so I'm going to shade here. So there were 2 ways that we did division. You'll notice I didn't force you to do it one way or the other. You could do long division, which is just like elementary school. What you're dividing by goes on the or what you're dividing goes on the inside. What you're dividing by goes on the outside. You multiply and subtract. We also did the synthetic division. Remember, with synthetic, you want the opposite on the outside, and you just use your coefficients. You add down and multiply up. A couple of things I do want to note on both of these types of questions is you have to have every exponent. So just keep in mind that you need every exponent from the highest to the lowest that you start with. And if you don't have one, put a 0 in as a placeholder. So for example, I have 5, 4, 3, 2, 1, and 1 without. That's how it should be. If I were missing like this 10x squared and it went 5, 4, 3, it skipped a 2 and went straight to 1, I would need to put a 0 where 2 should be. Okay, and that's true for whether you do long division or synthetic, as well as the next one, synthetic substitution. Both of those require all your exponents from highest down. All right, so the first one is simply asking you to divide. So if we did synthetic division here, on the outside, I do the opposite of this, right? So I'm going to say -5 out here. On the inside, I'm just going to use my coefficients. So my coefficients are 1, 9, 16, -10, 40, and my constant. I add down and I multiply up. So I'm going to add down, which is a 1, multiply up. -5 times 1 is -5. And I'm going to do that all the way down this particular question here. Remember to pay attention to your positives and negatives. Remember that you are adding down. So you are adding those positives and negatives down as well. Now remember, when you are dividing, you have to go back in and add your variables, okay? And so with synthetic, at the very end, the other little note you may want is you start your answer 1 degree less, all right? Which means when I plug these numbers back in, or plug these variables back in, I have a 1, I started with x to the 5th, I'm gonna start with x to the 4th here. Then I'm just gonna go straight down. This is my coefficient for the next one. -4 is my coefficient, plus 10, -10, and this is my remainder. So -9 over what I divided by, x plus 5. So this whole thing is my answer. So really the only difference between that problem and the words, the description that's used next where it says synthetic substitution, is you do not negate it. It actually gives exactly what you're going to use, which is that 3. Do not negate it. And your answer is only your remainder. I do not want the entire polynomial. Your answer is your remainder. And you will lose points if you write out that entire polynomial as your answer. So for synthetic substitution, you're going to do exactly the same thing. Do not negate what is given to you. It's a 3. Use your coefficients 1, -1, -12, 15, and your constant. Again, if I were missing one of those, 4, 3, 2, 1, and a constant, if I were missing any of those, I would put a 0 there. The process is the same. I'm going to add down, and I'm going to multiply up. So this process is exactly the same, but it wants to know technically what happens when I plug in a 3 to this polynomial. And so the answer here is just -8. So you could have higher exponent factoring, but don't let it throw you. It's the same as any factoring. I'm looking for factors of 12, or -12 rather, that add up to +1. What are factors of -12 that add up to +1? So I'm going to say +4 and -3. However, this is to the 4th power, so instead of x and x, I would say x squared and x squared. That's the only difference. All right.
Why'd you square the x?
All right, for the next group, I have given you the zeros, and I want you to give me the polynomial. So instead of factoring the polynomial and telling me what would make it 0, remember, I'm going to give you the zeros, and you're going to back into it. The only thing is that if you have a root or an I, you have to consider that it would have had a plus and a minus in that answer. So it's always x minus. So it's going to be x minus that -1, x minus that square root of 2, and it's always going to be the opposite as well when you have a root. All right? And I have to FOIL these. Now let me tell you, when I FOIL these, I always FOIL the ones that pair up first. All right? So these pair up nicely because remember, when you multiply conjugates, you end up with the first one squared minus the second one squared. So this is going to be a really easy foiling. I'm going to leave this alone other than to change it to x plus 1. And this is going to become the first one squared minus the second one squared. What happens when I square a square root? So this is just a 2. And I've already FOILed those last 2 groups. I'm not done. Now I need to FOIL these 2. And this is just regular foiling like we did in Algebra 1. X times x squared is x cubed. X times -2 is -2x. 1 times x squared is x squared. 1 times -2 is -2. Because you're in Algebra 2, my expectation is you know that I would not want you to leave the answer that way. We would want this in standard form. So I'm going to start with my highest and go down to my lowest exponent here. And I am done. By just the first term, what happens at the end of the graph? Yeah, so it is going down, and I know that because my leading coefficient is negative. And they are actually both going the same direction because my exponent is even. So if I were to ask what the end looks like here, you could draw it. They're both going down. Or you could say left side is down and right side is also down. But you're literally looking at your first number. Positive, it goes up. Negative, it goes down. And then your exponent, they go the same direction. So both up, both down, right? Or they go opposite direction. It goes up or it goes completely down. Those. What do you mean by positive? I am going to look at this. This number right here is a -1. That says leading coefficient. It's going to be one of these two. It goes down. Both of them down or down from left to right. All right. Then I just need to decide which of these. Leading coefficient is negative. The graph is going down. All right. Either both down or down from left to right. Then I look at the exponent on that same group. That's a 4. Even means they go the same direction. Both down. All right. Both down. I'm going to write an example of each one of these over here. So leading coefficient is positive and it is an even degree. That's something like 4x squared versus negative 4x squared. All right. This would be like 4x cubed versus negative 4x cubed. If there's already something on the outside, it is going to stay on the outside. So that 4 is going to stay on the outside. For the inside, I am going to use my factor tree. If it groups according to the index, remember with a radical, if you don't see an index, the index is 2. If it groups according to the index, you're going to take it out. If it does not group, it's going to stay in. For my variables, you can either just write it out as though you would. So like m squared is an m and an m. Or you can use the division. Divide by your index. 1 with the remainder of 0 means that 1 comes out. None stay in. So either way, you're going to get that 1m is on the outside. For the ends, I only have 1, so there is nothing to group with it. The n stays inside. We need to simplify. 4 times 2 is 8. My little note here said, if you have an even index, yes, I do. My index is 2. And I took something out that has an odd exponent. My exponent is 1. That is odd. Then in that situation, I need absolute value symbols on what is on the outside there. Only for my variables and only on the outside. If it were an odd index, I wouldn't even have to check for it, okay? But if it is an even index and you take a variable out that ends up having an odd exponent, you need absolute values because you cannot have a negative inside an even index. We did addition, multiplication, and division with radicals. For addition, you can only add like terms. Think of it like variables. For multiplication, whether it is distribution or foiling, you multiply your outside numbers, you multiply your inside numbers, but you never multiply outside to inside. For something like number 9, before I even decide if I can or cannot add them, I need to make sure they are simplified. Square root of 12 is not simplified. So I'm going to simplify it with my factor tree just like I did on the prior problems. 2 and 6, 2 and 3. I already have a negative out there. So when I take this 2 out, it needs to be a -2, a 3 on the inside, plus 3 square root of 3 minus 3 square root of 3. This is a nice one. These are actually all like terms. -2 plus 3 minus 2. My answer here is -2 square root of 3. Add like terms. If they were not alike, I would not add them. I would leave them the way they are. All right, for foiling, I'm going to do it exactly like I would, except I have to worry about the radicals. So square root of 3 times square root of 6 is the square root of 18. Square root of 3 times square root of 2 is the square root of 6. Before I finish up this problem, I need to see if they simplify. So I'm going to do my factor tree. This does simplify. A 3 comes out, a 2 stays in. This one will not simplify. It will stay a square root of 6. These are not alike. I am done. This is my answer. Next one is foiling. Very much the same, but the reason I'm doing it because I have coefficients on these. So for multiplication here, I have a -4, and the number on the outside across here is just a 1, so that's a -4. And then I have square root of 3 times square root of 3, which is the square root of 9, which is just 3. That is multiplication. I'm multiplying -4 times 3 there. When I FOIL the next place, I have -4 times -1, which is +4. And then I have the square root of 3 times the square root of 4, which is the square root of 12. All right, then I'm going to go to my next one, square root of 5 times square root of 3. And then square root of 5 times negative square root of 4 is negative square root of 20. Obviously, I want to simplify this more than what I have. I'm going to multiply the -4 and the 3. I'm going to simplify this. A 2 comes out, and I already have a 4 out. So I have an 8 square root of 3. This cannot simplify, so that is just the square root of 5. I'm going to factor tree this one.
Is 5 square root of 15? Yeah.
There we go. It helps to write the correct numbers. It also doesn't simplify, by the way, so it's still going to be square root of 15. That's 3 and 5. And then this is going to be 2 square root of 5. So when I look at this, none of these are like terms, right? And I'm done. I'm just going to box this and be finished. When it comes to radicals and division, you can simplify outside to outside and inside to inside, but you cannot simplify outside to inside. All right, so by that I mean, when I look at this one, I am going to say my 3 and my 2, could I simplify those? Well, they're both inside, but they don't reduce, so they just stay 3 and 2. X to the 4th and x squared. Yes, I can simplify those. They're both inside. I can divide both by 2 of those x's, by x squared, which means I just have x squared on top. My y's, can I simplify those? Well, yes, they're both inside. I can divide them both by a y, so that divides all of those, and I have 3 y's on top. So the first thing I'm going to do here is reduce it. Then I'm going to see if I can simplify the radicals individually, all right? Simplify the radicals individually. So on the top here, my 3 obviously is going to stay in there because it's a prime number. But my variables, all right, for my variables here, I have x and x, which means an x will come out. I have 3 y's. So if you were to do this little process here, you would see that a y would come out and a y would stay in, correct? And then I look at the bottom. On the bottom here, I have a square root of 2. That is a prime number. Nothing can simplify. All right. Still not done. My last step is to rationalize that denominator, meaning I don't want to leave a radical in the denominator, so I'm going to multiply the top and the bottom by that radical. So on the top, I still have the xy outside. I now have 3 times y times 2 on the inside, which is 6y. And on the bottom, I have just a 2 because I got rid of my radical. I cannot reduce the 6 and the 2. Yep. The 6 is on the inside, the 2 is on the outside. I cannot simplify those. I am finished. Whether it is a radical or an imaginary number, you want to multiply the top and the bottom by the conjugate of the denominator, which means just the opposite of the second term. The conjugate of this would be -3 minus the square root of 2. The conjugate of this guy would be -9 plus 6i. I only changed the second term, all right? Now on the top, I'm going to distribute if it's just a number, or FOIL if it's a binomial. On the bottom, I am multiplying conjugates. So reminder again, when you multiply conjugates, you get just the first one squared minus the second one squared. So when I look at number 13, on the bottom, I'm going to get the first one squared. Well, -3i squared is just 9. Minus the second one squared. If I square a radical, I get what's inside. So on the bottom, I have just 9 minus 2. Very nice. On the top, I'm going to distribute the 4. 4 times -3, 4 times negative square root of 2. And then I'm just basic adding and subtracting here, right? So I'm going to leave that -12 minus 4 square root of 2. And then I do the 9 minus 2, which is 7. If I wanted to reduce, it would have to come out of every outside number. Nothing comes out of 12, 4, and 7, so I cannot reduce it. This is my answer. For number 14, again on the bottom, I have the multiplication of conjugates. So the first one squared, 81, minus the second one squared, that is 36i squared. On the top, I'm going to FOIL. I'm going to multiply across 9 times -9, 9 times 6i, 5 times -5i times -9, and 5i times 6i. What is I squared? Who remembers?
-1.
Right, so this plus 30i squared is minus 30. This minus 36i squared is plus 36. And then I am just going to simplify those. Radical equations, your goal is to, as always, solve for the variable. With radical equations, you want the radical by itself, and then you're going to square it to get rid of the radical, and then you're going to solve for x, whatever method you need to solve for x. So you could have ones like 15 where you have the radical and a number, 16, two radicals equal to each other, or 17 where you have a variable and a radical. Anytime you see check for extraneous solutions, that means at the end of this process, you need to make sure that your answer works. So if you have something like 15, you're going to square both sides. You're going to end up with just what's inside. As you'll recall, squaring a square root gets rid of the root. On the right-hand side, you need to actually perform that square. So you're going to say 100 there. And then it's just a matter of solving. So solving the way you always do. And then dividing to finish it out. So all right. For something like this, you can check that 4, but really the ones that you need to watch are the ones like the third one where you have a variable that's been squared. Those are the ones that could potentially have a solution that does not work. Most of the time, assuming you did this correctly, this is going to work. You're not going to have an extraneous solution. The only time it wouldn't work is if you did it wrong. For something like 16, those are actually even easier because all that happens here is the two radicals get canceled. So we have what's inside over on the left. We have what's inside over on the right. And again, we are just solving. Variables on one side, numbers on the other. And then for something like 16, the setup is going to be exactly the same. You're going to square everything, but in this case, you end up with a variable squared. Remember, when you have a variable squared, you're going to get everything to one side and you're going to factor. All right, so anytime you see a variable squared and you're solving for the variable, you need to go back to your solving process. Solve by factoring, solve by the quadratic formula. Like those are really the two methods that you're going to solve by. And so you want for either one of those, they have to be equal to 0. I always make sure that my square is stays positive. So like for this, I would move the other two over. B squared minus 16b plus 60. This one is nicely factorable. So I am going to go ahead and factor this. Set them equal to 0. And I will see that I get 6 and 10. This is where you want to double check and make sure it doesn't cause any issues. So if I plug in a 6 to everything, that works. So I know 6 works. Then I'm going to plug a 10 in. So both of those work. They are both my answers. If either one of those had come out to where it didn't work, it gave me something like a false statement, then I would say that is extraneous. So chapter 8 all had to do with functions. We add, subtract, multiply, divide, and composite. So this is just 2 examples. This is addition and multiplication. I do want to point out the little dot is multiplication. On the next slide that we do together, it'll be an open circle, which means composite. So make sure you do those correctly. For addition and subtraction, you're really just looking for like terms. So I would just take the function and I would add to that the second function. So I'm just combining and putting in standard form, really. So the 3x does not combine with anything. -3 plus 3 actually zeroes out, and the x squared doesn't combine with anything. So this one's pretty straightforward. My answer is x squared plus 3x. Addition and subtraction is literally combining like terms. Multiplication is foiling or distributing, depending on what you have. This one wants us to multiply these two. Because it's multiplication, order does not matter. So I would typically put the smaller polynomial first so I can distribute each one. But you're just multiplying. So I'm going to multiply the -x through to each one of these. And then I'm going to multiply the -5 through to each of these. And then I would put it in standard form, combining any like terms. So I'm going to put the -x cubed first. It does not combine with anything. I'm going to look for x squared. So I have a 1x squared, a -5x squared. Combine my x's, -4x, +5x, and then -20. So that is my answer for multiplication. So with composite, you are putting one function in another, and order does matter. So when it says g of h, it means h goes into the g function. The first one just has a variable, which means my final answer will be a new function. The second one has a number, which means my final answer will be a number. So for the first one, I'm just thinking of it almost like substitution. I'm going to take this h function and I'm going to put it in to the g anytime there is a variable. So I'm going to say 3, and instead of t, I'm going to write negative t plus 4. And then I finish out that function, 3t minus 3. And then I want to simplify it, which just means distribute, combine like terms. And so this composite, the new function, looks like this. I'm actually done with that one. All right. However, when there's a number, you can either do that process and then plug in the number, or you can plug the number into the first function and take that answer and plug it into the next function. So the closest function to the number, plug it in, take that answer and plug it into the further function. All right, so if I were to do it that way, I would take the negative 4 and I would plug it into this g function. Everywhere there is a t. Then I'm just going to do order of operations. Negative 4 squared is positive 16. Apply that negative, that's negative 16. Plus 2 times 4 is negative 8. So I get negative 24 there. Then I would take that negative 24 and plug it into the f function. So t plus 1, negative 24 plus 1. My answer here is negative 23. So when you have numbers, you can plug it into the function that's closest to that number, take that answer and plug it into the other function, all right? If you had wanted to, you could have done what you did on number 20. You could take g and plug it in to f. So instead of t plus 1, you would get negative t squared plus 2 times t plus 1. And then you could plug in the negative 4 in to that. Either way, you're going to get negative 23 as your answer. So whatever function they give you, that g of x, f of x, whatever, just means y. So then you switch x and y. Wherever they are, you just switch them, physically switch them in the function. Then you work that function out to get y by itself. Solve for y. Get y all by itself. Once you have gotten that all by itself, you go back and put your function notation back in there showing that you have solved for the inverse. So this is just a y. So I am going to switch my x and my y. So I'm going to say x equals 1 over y plus 2 minus 3. And now I want to get y by itself. I'm going to do that first by adding the 3 over. So I have x plus 3 equals this. Now here's the little trick. Anytime what you're solving for is on the bottom and it's just one fraction and one fraction, or one term and one term, you can flip both sides. Anytime it's one term to one term, you can flip both sides. So I can flip this entire thing 1 over the x plus 3 and flip, I'll fix it. And then flip this one as well. Y over 2 over 1. So y plus 2 over 1, I can just write y plus 2, right? So anytime it is what you're solving for is on bottom, just flip both sides. Flip both sides and then solve. So now to get y by itself, I'm going to subtract that 2. Now listen, this guy is a group. I cannot take the 2 from the 3. It is 1 over x plus 3, and that whole group is subtracting the 2, right? And now I actually have y by itself. However, I need to somehow indicate that that is my actual inverse, which means instead of writing a y here, I'm going to write the g with the little prime there telling me that I found the inverse, okay? And that is the solution to that inverse. So the first thing we did with logarithms was just rewrite it. Remember, speaking of inverses, logarithms are just the inverse of an exponential function. Exponential functions are functions that have a variable in the exponent position. And so there are times when we need to solve for that variable, and you solve with logarithms using the inverse. For example, if I have x plus 2, I'm going to solve by doing the inverse of addition, subtraction. So if I have an exponential function, I'm going to solve using the inverse of an exponential function, which is a logarithm. And so the first thing we did was just make sure you understand how to rewrite those. If I have a logarithmic function like this, then I'm going to rewrite as an exponential function. My base is my base. Whatever the logarithm function equals, that is my exponent. And now that equals what was part of the function of logarithm. So for number 23, if I need to rewrite this in exponential form, my base is the 15. My exponent is the m, and 15 to the m equals 158. That is rewriting that. To go the other direction, I'm going to go from exponential to log. So I'm going to make this a log. My base is 17. I am taking the log of 82, and that equals the exponent p. Make sure when you write these that your bases of your logarithms are smaller, that you don't have some crazy thing going on, because it's going to cause a problem when you go forward and do solving. This next one says rewrite in exponential form and then solve. So to rewrite in exponential form, you need to have it equal to something. We're going to say an x, and we're going to rewrite this. Exponential form means 4 is my base, x is my exponent, and that equals 1 over 16. All right, so I just need to figure out 4 to what power equals 16. Well, 4 to what power equals 16 is just a 2, right? However, 16 is in the denominator. So what type of exponent tells me to put it in the denominator? Negative. A negative. So my answer here is -2. So the first one wants me to expand. I'm going to start expanding using the exponent first. I'm going to put that in front. So now I'm going to say 5 log base 2 of this. Then I'm going to use my subtraction. So I'm going to expand again. I'm going to say 5. It's multiplying both of them. So log base 2 of 8 to the 6th minus log base 2 of 3. I can still expand a little bit more because I have another exponent that can go in front of this one. So I have 5, 8, or 6 rather. Of log base 2 of 8 minus log base 2 of 3. And then that 5 goes to both of them. So you can actually just distribute this 5 to each log. So your final here, and I'm not going to make you do what your answer key shows. You can just leave it in expanded form. Which I don't think you'll have the answer key on this one. Technically 2 is to the 3rd power, so you could replace that logarithm with the 3, but this is your expansion. 30 log base 2 of 8 minus 5 log base 2 of 3. A couple things I want to point out is that you'll notice that I put my bases here. So you have to include whatever log base you had originally. It goes on every log, all right?
Channel 2.
And then take it one step at a time. It has to be fully expanded. If it's not, you don't get full credit. So then the other one is literally just the flip. They gave it to you in expanded form. They want it in condensed form. So I start again with what would be those exponents.
4.
Yep, I'm going to take the 4. I'm going to pull it up to the x. I take the 5. I'm going to pull it up to the y. So I have log base 3 of x to the 4th minus log base 3 of y to the 5th. I can condense with subtraction, can move to division. So then I can keep going, and I'm going to say log base 3. The first one should be your numerator. It should go on top. The second one should be your denominator. It should be on bottom. When you are completely done condensing, you should only have one log. If you have more than one log, you should be able to condense some more. And so this is my final answer for this one. So one of the things we know about logarithms is if you get them, or exponential functions, if you get them to the same base, then your exponents will equal each other. So you should be able to recognize when you have the same base of a number. So 8 and 2 have the same base. 27 and 3 have the same base. 125 and 5 have the same base, which is 5. And so this is already in its simplest form, which is 5. And I can rewrite this one as 5 to the 3rd power. Once I get it like that, I can just ignore the bases altogether, and I can say, well, the exponents themselves must equal each other. And then you have a really simple equation to solve. To solve for that variable, divide both sides by that 2, and my variable p equals 3/2. So the next one is a change of base formula, meaning let's say I do need to solve for a logarithm and I don't know the base. Then I can solve using change of base, because remember on your calculator you have log, common log, which is a base 10, and you have ln, natural log, which is a base e. Neither one of those are base 2s. And 2 is not a perfect base of 58. If this was log base 2 of 8 or 16 or 32 or 64, it's a perfect base. And you could potentially calculate that without a calculator. But 58 is not a perfect base 2, which means you're going to get some crazy decimal. So you're going to calculate it by using your change of base. Change of base is really simple. In your calculator, you're just going to take your common log of the 58, that big number, and you're going to divide it by the common log of your base. And that's going to round to the nearest 10,000 as it recommended there. And we're going to say, or this one's nearest 1,000, so 3 decimal places. Literally just make sure you know how to use your calculator if you have a base other than 10 or E. So the goal here, whether you're solving exponential functions or logarithms, is to get the base by itself, whether it be the exponential base or the logarithm. You want the base or the logarithm by itself, which means get rid of everything that is not it. So for number 30, you're going to think of solving as though you want to get this piece by itself, okay? The 10 to the 7p. You want that by itself first, all right? Which means I am going to subtract the 9 over. So now I have 10 times 10 to the 7p equals 25. You cannot multiply those 10s. It is 10 to a power, not just 10, okay? So now my next step is to get rid of what's being multiplied. Get rid of this guy. I am trying to get the 10 to the 7p by itself. All right?
Yeah.
And now I'm ready to solve. So to get rid of a base, you use a logarithm of the same base. This is nice because they gave us a base 10, which means I can take the log of both sides. So I am going to log both sides. Whatever you do to one equation, you have to do to the other side of the equation. What's nice about this one is bases cancel out bases, meaning this log base 10 and this exponent base 10 will cancel each other out, and I am left with just the exponent. On the right-hand side, I have this number here, which I'm going to leave alone for right now, just as log of 2.5. And then now I just have a basic equation. I'm just solving. So I'm just going to divide both sides by that 7. So in your calculator, you can now do log. It's going to open a parentheses, 2.5, close parentheses, divide by 7, and it wants you to round to the nearest 10,000th. That is 4 decimal places. So look at your fifth and round the fourth one based on that.
That was 2.5.
So when you are solving logarithms, get the log by itself, add anything over. Bases cancel out bases. It was a log base 2. That means 2 to the power, 2 to the power. Cancel. 2 to the negative 2 is 0.25. Add the 2 over. Your final answer, 2.25. So my first step here is factor. You are going to take the common factor out, which is your m. You're going to be left with m squared plus 3m minus 4. So that's factors of 4 that subtract to give you 3. So m plus 4, m minus 1. All right, so that's my factoring on top. On bottom, my common factor is a 2. And I'm left with m squared minus 4m minus 32. Which means that I am looking for factors of 32 that add up to 4, or subtract to give me 4, whether. So I'm going to say m minus 8, m plus 4. So your first step is to factor. Typically at this point, I will do excluded values, right? Because this is the easiest time before you start canceling to figure out where the denominator is 0. So my excluded values would be where every group is 0. If your common factor was a number, that will never be 0. So ignore that one. It will be 0 here at 8. So part of your excluded factors will be that m cannot equal 8. It also would be 0 in the denominator if this was equal to 0, which would be at negative 4. So my excluded values are negative 8 and 4. Okay? Now I'm ready to cancel and figure out what my simplified polynomial or rational setup looks like. The m plus 4s cancel. And that's really the only thing that will cancel. So simplified, it will be m and m minus 1 on top, and 2 and m minus 8 on bottom. So I have my simplified rational expression and my excluded values for that. So multiplication and division are really exactly the same. The only difference is that before you start with your factoring and canceling for division, you need to keep change flip. Other than that, it's identical. So for this first one, I'm going to keep the first one exactly the way it is, and I may factor as I go. So like for this, I would probably do x minus 8, x plus 7 over x plus 7. Flip this guy, x minus 6 over 7. Any top can cancel to any bottom once it is multiplication. Once you have done your keep change flip. So my x plus 7s cancel. What I do is I check every single piece of it to make sure that I haven't forgotten anything. So the x minus 8 will not cancel. The x minus 6 will not cancel. Those will remain on top. And on bottom, the 7 will not cancel. So that is the only thing left on bottom. And that's my answer. If you have multiplication, you don't have to keep change flip. You go straight to factoring. And so for this one, I'm going to go ahead and go straight to my factoring. I have a 10x and an x plus 6. I have an x minus 10. This is already factored. And so for this one, really, I can cancel those 10s. And that's about all that happens here. Nothing else is going to cancel. So on top, I still have the x plus 6 and the 8. On bottom, and I actually took out a 10x, so we're going to cancel him too. On bottom, this x and x will cancel, so I have just the x minus 10, and I am done. So 10x and 10x canceled. Nothing else really cancels there. And I am making sure that I've accounted for every piece of it, and you are finished. So obviously with addition and subtraction of any rational, whether it just be fractions like 3/4 or rational expressions like these, you need a common denominator. If it has something in common, that's great. If not, you can think of it as the butterfly method, cross multiplication, meaning you can multiply if it'll let me, you can multiply each group across. So what's basically going to happen is it's going to be the 2 times the 4k minus 6, and then you have a plus, and it's going to be the 3 times the 15k plus 12. That is going to be my numerator. My denominator is going to be the multiplication of these two. So 2 and 15k plus 12. And we will do some simplifying at the end. Or if you can simplify before, that's fine, but I would recommend you do it all the way out and then simplify, because you may mess up if you try to eyeball it. So I'm going to distribute these and combine my like terms. So I have 8k minus 12 plus 45k plus 36. All of that is over. I'm going to go ahead and put this through because I don't know that y'all will see what I'm going to show you in just a second. Now, I want to point out that you cannot cancel these two. That is, everybody often will say, oh, I can cancel these and I can cancel a k. You can't cancel a piece of it, okay? You have to be able to take it out of everything. So this is why you want to keep simplifying and then see, is there anything that comes out of every single number that I have? So if I were to continue here, I'm going to do my like terms. So I have 8k and 45k. I have negative 12 and positive 36. And then on bottom, I have the 30k and the 36. So if I look at all four of those numbers, nothing comes out of all four of them, right? Nothing comes out of 53, 24, 30, and 36. If that were a 54, I could reduce here, okay? Because something comes out of all four of those. But that 53 boots me being able to reduce anything. Nothing will reduce. This is my final answer for this one, okay? I did a subtraction. Subtraction works exactly the same. But I did this because a lot of people often don't distribute their negative correctly. So if we look at this one, again, you can do that, what's called a butterfly method, where you just multiply across, right? Or the cross multiplication. For this one, they are both binomials. So you want to group those because you're going to end up foiling. Put your subtraction sign here. And then you have that 5x times the x plus 6. Your denominator is going to be those two groups. You do not have to FOIL the groups. You can leave them the way they are on bottom, but on top you need to FOIL and simplify. So for that denominator, you're welcome to leave it in factored form, but on the numerator, I need you to FOIL and combine your like terms. So we are going to FOIL that x through and that 4. Here you are distributing that negative. So 5x goes through with the negative. 5x goes through again with the negative. That's the most common mistake there, is that negative. The bottom can stay, like I said, leave it in factored form. No reason to FOIL it. All right. And then we are going to combine our like terms. So 5x squared and negative 5x squared actually cancel each other out completely. I have a negative 6x, a positive 20x, and a negative 30x gives me a negative 16x. Then I still have that negative 24. On bottom, again, you can leave it in factored form. Nothing comes out of all of these. So this is my answer. I am finished. So for this, I gave you two different examples of what you could have for solving. Your goal is to get rid of all your denominators. So the first thing you need to do is find the common denominator between b squared, and 6b squared. Your common denominator is 6b squared, right? For something like more complicated, like 38, what I typically do is I write out, okay, that denominator is k minus 2. What would this look like factored? Well, that's k minus 2. What would this look like factored? K minus 2, which shows you your common denominator is that k minus 2. All right, so finding the common denominator is your very first step. And then basically what happens here is everything cancels in the denominators. And you just multiply the numerator by what it did not have or what would cancel there. So like if I'm going to multiply this by 6b squared, what really happens is the b squareds cancel and I just have 1 times 6. Here, I multiply by the 6b squared. Well, the b squareds cancel and I have 6 times that b minus 3. Plus, I multiply by 6b squared. The whole thing cancels. I have nothing left over, so it's just the 1. And then you have this pretty simple equation to solve. The same thing actually happens on the other side, and it looks like it would be way more complicated, right? But it's really not. If I multiply this by k and k minus 2, that cancels. I'm left with 1 times k. Plus, if I multiply this by k and k minus 2, actually the entire thing cancels, and I just have a 5. Over here, if I multiply this by k and k minus 2, this whole thing cancels and I have this polynomial. And again, I have something to solve here. Whether it be a quadratic that I'm going to set everything equal to 0 and factor, or whether it be a really basic one where I just solve for the variable. So like for this one, I can go ahead and look at this and say b cannot be equal to 0. So as long as I get something not equal to 0 as my answer, I'm good to go. Here, what would make this denominator 0? Well, 0 or 2 would make that 0. So k cannot equal 0 or 2. Always look at that common denominator and it will tell you, where would your denominator equal to 0? Those are the two I can't have. As long as I get anything other than those numbers, I don't have extraneous solutions. On here, SOHCAHTOA. Hopefully y'all can do this in your sleep. Sine is opposite over hypotenuse, cosine adjacent over hypotenuse, tangent opposite over adjacent. Below that I gave you reciprocals. Cosecant is just the reciprocal of sine. Secant is the reciprocal of cosine. Cotangent is the reciprocal of tangent. So as long as you have the SOHCAHTOA piece, you will be able to get all 6 of them. What I always do also tell you is that you want to make sure that you are labeling accordingly. Meaning if that is my angle, my hypotenuse is always opposite my right angle. And then across from the angle is the opposite side. One that touches the angle is the adjacent side. I am then going to use the function that they gave me. They want cosecant, which is the reciprocal of sine, which means I need my opposite and my hypotenuse. They handed me this one. I don't have to use Pythagorean theorem. I have the 2 sides I need. Sine would be opposite over hypotenuse, so cosecant is going to be hypotenuse over opposite. I am done. Honestly, number 40 is identical to number 39. They just didn't draw a triangle for you, okay? They said find the cosine if secant is theta. Well, secant is the reciprocal of cosine. They were very nice to you right here, right? Yeah. But even if they weren't nice, if they gave you secant, they gave you the hypotenuse and the adjacent side. So label what they gave you based on the trig function. And then over here say, well, what do I need? Well, I need the adjacent and the hypotenuse. Look at that. I have everything I need. If I didn't, I would use Pythagorean theorem to solve for the third side, and then I would just fill it in. For this one, all I have to do is flip him. However, one little caveat, because I have a radical on the bottom, I am going to have to do this, but other than that, I am finished with that one. All right, value of each. Secant is the reciprocal of cosine. On your calculator, you do not have secant. So in your calculator, you would say 1 divided by cosine of 30. And it's going to ask for it as a decimal here. So you are literally rounding to the nearest 10 thousandths. When you are solving for an angle, you are going to use your inverse trig function, which means you are still going to label this angle, this triangle, according to that angle. And then you're going to say, which two sides do I have? I have my opposite side and my adjacent side, which means I need to use tangent. But because I'm solving for the angle in my calculator, I'm going to use inverse tangent of the opposite side divided by the adjacent side. They want to the nearest angle. I'm going to do that, and I'm going to make sure my calculator is in degrees, not radians. When you are solving for a triangle, yes, you can use law of sines, but if it's a right triangle, you can use SOHCAHTOA. You can also use Pythagorean theorem to solve for the third side. You can use the fact that once you solve for one of the angles, all of them should add up to 180. So solving for a triangle just means I need every side and every angle. So the first thing I would solve for here is that side. I would use Pythagorean theorem. Keep in mind you have, like for example, I would pick an angle and just label the whole thing according to that. So I have the hypotenuse here, I have the adjacent here, and I have the opposite, which means to solve for Pythagorean theorem, I'm going to say the one I don't know plus the side always equals the hypotenuse. And then round to the nearest tenth, which means your side length that you're looking for is approximately 7.3. Then all you have to do is solve for one of the angles, all right? I would solve using the sides that were handed me, not the one I rounded. So if I wanted to solve for A, I would use adjacent and hypotenuse, so I would use inverse cosine here. Adjacent divided by hypotenuse, and I would get that angle measure. And then once you have that angle measure, use the fact that they should add up to 90. And so now to solve for B, I'm going to say 90 minus 54.7 and get my B degrees there. So I have solved for all three sides and all three angles. Then we have standard position of an angle. Remember, standard position means that I start on the positive x-axis here, and I go counterclockwise. So this is one ray of my angle. And then I'm just going to go to approximately 250. I am not going to get something out a measure, but you need to remember that this is 90, this is 180. And so to get to 250 from 180 means I need to go about 70 more degrees, right? So I'm looking that you know where it is and what direction you go to get there. We also learned about coterminal angles. That just means they end at the same spot. So they have given me an angle. An entire circle is 360 degrees. And so I'm just going to take what they gave me and add 360 and subtract 360. So to get my positive angle, I'm going to say negative 325 plus 360. That's a positive. To get a negative coterminal angle, I'm going to subtract that 360. And there's my negative. Have standard, any terminal point on the coordinate plane that is not unit circle, meaning my radius is definitely not a 1 here, then you can calculate it. First, calculate your radius with the square root of x squared plus y squared. That's based on the Pythagorean theorem. And then your sine is y over your r, cosine x over r, tangent y over x. And then your reciprocals work exactly the same. Cosecant is the reciprocal of sine. So it's going to be, as I wrote it incorrectly right here, r over, I wrote both of these, all of these exactly the same. So You want r over y, r over x, and x over y. You are basically just seeing which one do they want. If they ask for tangent or cotangent, you do not have to calculate any type of r, right? If they ask for one of the other four, you do need your r. And in this case, they asked for secant, which is my reciprocal of my cosine. So for secant, I need my r and I need my x. All right? So the first thing I want to do here is I want to solve for the r. I want to take the square root of the negative square root of 11 squared plus the negative 5 squared. You can actually ignore the positives and negatives when you're doing your r, because when you square it, it's going to get rid of it. So I have 11 plus 25, which means I have the square root of 36. Your r is always positive, so my r here is 6. Then I am going to just fill those in. I need r over x. So I do need to get rid of that radical in the denominator. So my answer here is negative 6 square root of 11 over 11. Converting degrees to radians, radians is degrees. If I am in degrees and I want it in radians, I'm going to multiply by pi over 180. And then I do not want decimals here, so just reduce your fractions. Go ahead and get rid of the zeros. Those are easy. 15 and 18 reduced by a 3. I would also say number one mistake is that little t tiny negative right there. So negative 15 reduced by 3 is negative 5. Make sure you make him painfully obvious or you will forget that negative. So my final answer here is negative 5 pi over 6. I'm going to do the same process to convert the other way, except I'm just going to flip it, which means I am going to multiply by 180 over pi. And again, your pi's will cancel here, always, as it should for this if it had pi to begin with. And then reduce. 6 reduces to 180 by 30. And then you're going to multiply across. You're in degrees, you should be 210 degrees. All right, so the key here is just the angle times the radius. However, little caveat is the angle has to be in radians, which means I have to do that conversion. So if you happen to know that 60 is pi over 3, you're good to go if you know your unit circle. If you don't, or if they don't give you a common angle that you would know, then you're just going to say whatever the angle measure is that they gave me times that pi over 180 to convert it, and then multiplied by that radius. That's all you're doing here. So it's all multiplication, which means I can do all of my canceling from any top to any bottom. The 60 actually completely cancels with the 180 with a 3. If the 3 and the 16 reduced, I could reduce those as well, because bottom to top, they don't. So I can just multiply 16 pi over 3. That's all I'm looking for there. I mean, if you want to put the units, you can, but that is what I'm looking for because it said leave it exact. If it wanted it rounded, you would plug that into a calculator, you would round it, okay? So the last thing we did was we graphed. So amplitude is the absolute value of A, period is 2 pi over B. Technically that's an absolute value too because your period is how long it takes something to do it. So A is the number in front of the trig function. B is the number in front of the theta or the variable. Keep in mind, you could also rewrite this sign as y equals 4 sine of 1/2 theta, meaning that A is 4 and B is 1/2. So if I am answering the question for 50, my amplitude then is going to be 3, and my period is going to be 2 pi over 2, which simplifies to just pi. For number 51 then, my amplitude is going to be 4, and my period is going to be 2 pi over 1/2. Keep, change, flip, that simplifies to 4 pi. So My period tells me I'm going to start all of these because I don't have any left-right shifts at my origin. So for this sine graph, I'm going to do. All right, what I want to do here is I actually want to rewrite one of these to cosine because I want you to see both of those graphs. So rewrite this one to the cosine so that I can show you both of them. All right, just in case you have one or the other on your exam. So we're going to just ignore that and we're going to say 3 cosine. The period tells me how long it's going to take for this to go through an entire cycle. So I am going to always start at the origin since there's no shifting that way, and I'm going to end at whatever my period was. All right? That is true for both of these. I'm going to do start to end. I'm going to cut it in half, and then I'm going to cut it in fourths. So I should have 4 quarters here. First, second, third, fourth here. All right? The same is true whether it's sine or cosine. Y'all are going to start at the origin. You're going to end the period. Tells you to end 4 pi in this case. Cut it in half. And then cut those in halves to get your quarters. All right? And then it's just a matter of plotting your points. You need to make a note of where your highest value should be based on your amplitude and where your lowest value should be based on your amplitude, which in this case, 3 and -3. And then I'm going to graph it. So here, cosine starts at the highest point. At fourth quarter, you're at your midline. At first quarter. Halfway, you're at your lowest point. Third quarter, you're at your midline again, and you end always where you started. That's what a period tells you to do. And then you just connect those with your curve. Arrows at the end tell you that this is a continuous infinite function. The same thing is true for sine, except I start and end at different places. I am going to note my highest value and my lowest value. And then I am going to do the sine graph. Sine starts at the middle. At first quarter, it is at the highest point. Halfway through, it is back to the middle. Third quarter, it goes down to the lowest point, and you end where you started. And then once again, you are going to connect those with your curve.